The universal wave equation is a very important equation that actually tells us, essentially, the speed of a wave if we know some of its characteristics. To come up with this equation, let's start off with what we know as speed. We know that's just distance per time. And our units for that are meters per second. So the question is, how can we come up with this equation, or how can we modify this equation for waves? Do we know anything that relate to meters or seconds for waves? And there are a few characteristics of waves that we talked about in the previous lesson that can help us out here. For example, we know that frequency is just the number of cycles per second, right? Or the number of cycles per time. So that's nice because it sort of establishes time in this meters per second that we're trying to achieve. The other thing is meters. What property of waves include meters? The answer is the wavelength, right? A wavelength is just the length of one wave. So this is basically just the meters, right? Or the length per one cycle, right? That's essentially what wavelength is. It's the length of one cycle, meters per cycle. So notice how with these two things, we have meters and we have seconds, and we have cycles there and there. So how can we arrange these two to come out with meters per second? And it's not actually that hard. If we look at this like this, number of cycles per second, and we multiply, I'm going to move this. Oops, didn't mean to duplicate it. I'll erase this version of it. Move that over. And we multiply this by meters per cycle, you see that essentially the cycles cancel out and we're left with meters per second as our units. We're doing a little bit of unit analysis here. So essentially what we have to do to find the speed of a wave is, if we know the frequency and the wavelength, all we got to do is realize that the speed is just the frequency times the wavelength. And if you can think about this, you can think about the speed as like sort of how much of a wave passes in front of a point every second, right? Or how many meters of a wave pass in front of a point a second. And if you think about it, that's sort of where this relationship comes from. So we can always figure out the speed of a wave if we know the frequency and the wavelength. If we want our units to come out to meters per second, obviously our wavelength should always be in meters, and our frequency should always be in cycles per second, or hertz, as we like to call it, okay? That equation there is called the universal wave equation. So we're actually going to skip down here to problem 1 and see if we can figure out the speed of the wave. So calculate the speed of a wave. It has a frequency of 440 hertz and has a wavelength of 0.7 meters. So 440 hertz actually is middle A in music. That's our baseline frequency that we use to establish all the other notes. So we know the speed of a wave is equal to the frequency times the wavelength. And in this question, we know the frequency is just 440 hertz, or I'm going to write cycles per second, just so we can see the units cancel out. All right, cycles per second times 0.7 meters per cycle, because that's what a wavelength is. It's the length per cycle. You see cycles cancel out, and we're left with the answer, which in this case, to 3 significant digits, ends up being 308 meters per second. This is probably in air. About 300 meters per second is about, that's roughly sort of the speed of sound in air. So it sort of makes sense as a number. Think about it, that's pretty fast. Every meter the sound travels 300 meters, but it's also not super fast. It's nowhere close to the speed of light or anything like that. Let's try the next question. Calculate the frequency of a sound wave traveling through 30 degrees Celsius air if the wave has a wavelength of 20 meters. Okay, so in this question, we're looking for frequency. So if we rearrange the wave equation, we're going to get that frequency, take out the pen, frequency equals speed over wavelength, right? If I just divide both sides by wavelength. Okay, so we know the wavelength of the wave, it's given in the question, but we're missing the speed. The key here is that it tells us that it's in 30 degrees Celsius air. And the thing about air is that sound travels pretty predictably in air. If we know the temperature of the air, we can calculate how fast sound will travel. So going back up to the top, we have a space for this. Explain how you can calculate, question 2 is, explain how you can calculate the speed of sound in air at different temperatures. So scientists basically did a whole bunch of experiments and calculated the speed of sound at 0 degrees Celsius, at 1 degree Celsius, something like that. They came up with an empirical relationship between the temperature and the speed of sound. And the equation that's on your formula sheet, which is the one we're going to use, is V, I'm going to call it sound in air, is approximately equal to, little squiggly equal sign. This isn't exact, it's an approximation. It depends on more than just the temperature, but we're just sort of just guesstimating at this point. So it's approximately equal to 331 meters per second plus 0.59 meters per second per degree Celsius times the temperature. And that is the temperature in degrees Celsius. That's why I put the little C there. And also why in this constant term, the degrees Celsius, I show the degrees Celsius there. So essentially what you have to do to calculate the speed of sound in air is plug the temperature of the air into this formula. So it's 331 plus 0.59 times the temperature. The degrees Celsius should cancel out with whatever you plug in here, and you're left with just meters per second. So what does this equation actually tell you about the speed of sound in air? What happens as we increase the temperature? You should notice that as you increase the temperature, every degree Celsius you increase the temperature, you're raising the speed of sound in air by about 0.6. So you're actually getting faster. The sound travels faster in air the warmer it is. Think about why that is, and we'll actually discuss in class the reason for that. So back to our question. We can now, in order to solve this question, remember we were missing the speed of sound in air. We have the wavelength, but we can calculate the speed of sound in air using that formula. So let's do that now. So the speed of sound in air is 331. I'll just use the units here just so we make sure we don't make a mistake, plus 0.59 meters per second per degree Celsius times the temperature is 30 degrees Celsius, which comes out to, if I do that calculation, 331 plus 0.59 times 30 is 348.7 meters per second. Note how this term actually has only two significant digits. So really, the calculation that comes out to this should only have two significant digits. But because it's an estimation anyways, I'm okay if you take it to three significant digits. That's pretty typical. So we can say that this is about 348.7. We'll carry that through, but at the end of the calculation, we'll round to three significant digits based on that. So anyways, we now know the speed is 348.7 meters per second. We know the wavelength is 2 meters. The meters are going to cancel out. And the frequency is going to be 348.7 divided by 2, which is 174.35. Sorry about the fact that we're running into this thing here. And what's the units for that? Well, if you look at it, it's like per second, right? Something per second. And the thing that we often don't include when we include the wavelength is this is really the wavelength per cycle, right? And if you simplify the units there, basically this would simplify as cycles per second. So really the answer, rounded to three significant figures, is 174 hertz. And I realize now that this actually only has two significant figures, so possibly we should round our answers to approximately 170 hertz. Okay, two significant figures. There we go. So whenever you're not given the speed of sound, but you know it's in air and you know the temperature, you can always calculate the speed of sound through that air. This one's a little bit more straightforward. I think you can probably do this one yourself. Pause the video here, try it yourself, come back to it to see the answer. So rounded to three significant figures, the answer should be 0.535 meters per cycle. So one thing to note for this, you don't actually need to put the per cycle when I ask you to calculate the wavelength. If you just put 0.535 meters, I would have been absolutely okay with that. Again, I'd encourage you to try all these questions before seeing me do the solution. So pause the video here, try it yourself, and I will go through it when you unpause, just in case you get stuck. So for this question, the period of a wave from a piano is 1.2 times 10 to the negative 3. If the temperature is 10 degrees Celsius, what's the wavelength? So we can assume that this wavelength, or this wave, is traveling through air because it gives us the temperature of the air. And we need to calculate the wavelength. So if we look at the wave equation, V equals frequency times lambda, right? Our wavelength is just going to be equal to our speed over our frequency. Now, in this question, we actually don't have either of these things, right? What are we given? We're given that the temperature of the air is 10 degrees Celsius. So off to the side, we know how to do that. We know how to calculate the speed of sound in air if it's 10 degrees Celsius. So let's do that first. That V is equal to, or I should say approximately equal to 331 meters per second plus 0.59 meters per second per degree Celsius times 10 degrees Celsius. So if we do that, we get that the speed of sound in this air is approximately 316.9 meters per second. But we also don't have the frequency. So we now have the wavelength, or sorry, the speed. We need the frequency. We are given, however, the period. And remember, there's a relationship between period and wavelength. Remember that if we want to calculate the frequency, let me just erase that. Want to calculate the frequency, it's just going to be 1 over the period, right? So we know the period is very short. It's a very quick wavelength, probably a very high pitch. 1.2 times 10 to the negative 3 seconds. So if we do that on a calculator, you just literally do 1 divided by that, 1.2 times 10 to the negative 3, you get a frequency of 833.33 hertz, basically. Okay, so there's our frequency. Now we know that as well, so we can plug those into our calculation and solve. So our speed is 316.9 meters per second. Our frequency is 833.33 hertz. And if we do that calculation, it should spit out close to that answer, 316.9 divided by 833.33, about 0.38. And, rounded to 2 significant digits. Yeah, we can do it rounded to 2 significant digits, is 0.38 meters is the wavelength. Okay? So this next question I encourage you to try by yourself, once again. But one thing that you may need clarification on is, what is an MHZ? We know HZ is hertz. What does the capital M stand for? Well, if you remember our metric prefixes, the capital M is mega. So what this is actually a megahertz, which you may have heard that term before. But what that means is 1 million hertz. Mega is a prefix for a million. I remember it because mega and million both start with M. So 10 megahertz really just means 10 million hertz. So it's a very, very, very fast frequency, very high-pitched frequency. If you were to hear it as sound, you wouldn't be able to hear it as sound. It's way too high-pitched. And the period of that is going to be very, very, very short, right? This is what we consider in the ultrasonic range. Ultrasonic is anything above regular human hearing range. So now that you know that, you should be able to solve this question. And if you do, your final answer, I'm not going to do the solution here because I think you can do it yourself. Your final answer should be to 2 significant digits, 3.2 times 10 to the negative 5 meters. Okay? Try it yourself. So in this question, we have a bat that's using echolocation. There we go. Luckily, this app has built-in bats. And then there is a insect that is chasing. I'll just do an insect, like little wings like that. So bats basically emit sound, and basically what they're listening for, they listen for when that sound returns to them. And that tells them sort of how far away the insect is. This is called echolocation. And they have super sensitive sound to hear this in dark, when eyes wouldn't be much of use. They use echolocation. Really cool. So basically, if we know some stuff about the waves that the bats use, we can maybe do the calculation that the bat's able to do in its head. So first of all, we're asked to find the distance. So this distance here, that's what we're asked to find. We know the air has a temperature of 20 degrees Celsius, so we can probably use that to find a speed of sound. But how can we do this calculation? We're also given a time as well, right? Well, this is the thing. We have an equation that relates distance and time, right? And it has to do with the speed, right? We know the equation for speed is distance over time, right? So if we know the speed that this sound travels at, we know the distance, so we're trying to find the distance actually, but we know the time that it takes, we can actually calculate how far away the insect is. So the key here is that, so you think you might just want to plug in the speed of sound and time and solve for D, but there is a little bit of a trick. How far does the sound actually need to travel? Well, first it needs to travel, the bat emits it. It travels to the insect and back to the bat. So really, the total distance it travels, if we call the distance to the bat, between the bat and the bug, D, the distance it travels is actually 2D. Is 2D, right? It's 2 times the distance. So let's use that in our equation. Also, let's calculate the speed of sound at that temperature. So 331 meters per second plus 0.59 meters per second per degree Celsius times 20 degrees Celsius. That's going to give us a speed of sound of 331 plus 0.59 times 20 is 342.8 meters per second. And now we can plug that into our equation, right? We're sort of running out of space here. I should have given you more space. You know what? I'm just going to move this over here. 342.8 meters per second, and I'm going to erase that to give us lots more space over here. So if we do this calculation here, the distance it travels, well, we don't know. We're going to solve this equation for D, right? Let's plug in what we know about the fact that it's going to be 2D is our displacement over delta T. Now we can solve for D, right? If we solve for D now, we're going to get D is equal to V delta T over 2, right? And then if we do that, our speed is 342.8 meters per second times the time, which is 0.017 seconds, all over 2. If we do that calculation, 342.8 times 0.017 divided by 2 is 2.9 meters away. All right, so the total distance that the sound had to travel was twice that far, but we took that into account when we replaced it with 2D in our equation. These next 2 questions make use of similar principles. I want you to try those yourself. Come to class tomorrow and we will take them up. All right, but really give them a good effort yourself.